Hello, Alka. I'm audible.
Yes, sir.
Okay. Should we start?
Okay.
Yeah. Okay. Okay. So this is week 4, and live session is from 6 to 8. And I'm Jyoti Sharma. And here is my brief introduction. So I'm a PhD student right now, doing PhD in Earth and Environmental Sciences from ISL Bhopal, and I had MSc in Environment Management from FRI Dehradun and BSc from University of Delhi in Botany Honors. And because I'm a PMRF, that's why I have liability and the responsibility to teach you people. So I'm here with a lots of questions. So again, this will be the strategy how we will go on. I have a lots of MCQ questions, and we will try to solve it by the discussion. And your participation will be highly valued. So let's start. Uh, Okay, so uh, as because it is a week 4, and in week 4 from lecture 16 to 20 it has been covered. So mostly we will talk about the Gaussian dispersion model for point source, for line source, and for the area source. Okay, then we will not go on the numerical questions, but we will talk about the assimilative capacity of the airshed and the emission inventory. So first, you must know about the Gaussian dispersion model. What's the assumptions we have for point source, for the line source, for the area source? What different equations we have for this Gaussian dispersion model, and what assumptions we have, how we can calculate our concentration. So let's talk about it. Mm. Okay, before going to MCQ questions, let's spend 5 to 10 minutes about this Gaussian plume model so that you can give me answer very rightly. This is basically this is the diagram based on which we have the Gaussian plume model. So here you can see that we have a stack. For example, we have a chimney. Out of that chimney, there is a plume that is or gas that is emanating from that chimney, so we will call it as a plume. So we have chimney that is known as also the stack, out of which plume or let's say smoke is emanating. So we will call it as the plume. So and the structure of this plume is, we are assuming the conical structure. Okay, and then this plume will rise. Uh, in spite of this stack height. So we have two type of height. The one is stack height, for example, the chimney height, and the second rise is plume rise. Plume may rise because of the momentum, because of the buoyancy. Okay, because of the velocity with which this smoke will come out from the chimney, and secondly from the temperature differences. Okay, so the plume will rise. So whatever the plume will rise plus your stake height will give you the effective height. Okay, so here we can see H plus delta H. It will give you the capital H, that is the effective stack height. So the variable right now we have is the capital H. So it may be that in some numerical question we have only the stack height and we have to calculate the delta H. So we have some kind of formula by which we can calculate this delta H or the plume rise, and whenever we will do the summation of this delta H with the stake height, then we will get the effective stake height. Okay, so this is related to your height. Then we have the wind speed. If you people have the value of the wind speed, we will also see we mostly we have the instrument at 10-meter height. Okay, or let's say at the height of the stake, but we want to calculate this wind velocity at the height of the effective stake height. So how will you calculate it? Okay, so you will have to calculate wind speed at that height. First thing. The second thing is you may also have to calculate the effective stake height if you have given this stake height only. This is the second thing we have to consider before going to the equation of this plume Gaussian model. Okay, the third thing is, here you can see this delta x, delta z, sorry. So this delta z is nothing but this is the standard deviation. Just keep in mind, whenever the plume is coming, it will spread horizontally and the vertically. And we are assuming that at the center line we have the maximum concentration, either it is horizontal or it is a vertical. So but it will dilute or it will disperse horizontal as well as the vertical. So how much it is dispersing, we will calculate it as the standard deviation in the horizontal direction and in the vertical direction. So if we are talking about this z means the standard deviation or the dispersion in the vertical direction. Okay. And if we are talking about the delta y, then this is nothing but the standard deviation or the dispersion of this plume in horizontal direction. So here we can see that if wind is moving in x direction, means our plume is going in the x direction, but this will disperse in the y direction as well as in the z direction. Z means vertically dispersing and y means horizontally dispersing. So whenever it is dispersing, then we will call it as the standard deviation. So standard deviation in horizontal direction and in the y direction. And we also have to calculate it. So we have three terminology here: the wind speed at that height, the stake height or the effective height that we have to calculate, and the standard deviation in horizontal as well as the vertical. So if we have these three values and some more values, then we can calculate our concentration, like uh, concentration at some receptor. For example, if we want to calculate how much concentration we will have at 10-meter height, or in the direction of 10 meter apart from the chimney. For example, there is a your chimney and you want to calculate from that chimney, there is a distance 10 meter. So at that 10 meter distance, how much concentration you will get of that plume, or for example of that smoke. Okay. So how we can calculate this? Firstly, you have to calculate the plume rise. So there are some formulas. There are various formulas to calculate this plume rise, and one of the famous is delta H. This delta H, that is the plume rise. This will equal to 150 multiply by F upon mean velocity. There is a cube of that mean velocity. If you have the wind velocity or the mean velocity, this is okay, but here F is the buoyancy flux parameter. Okay. And this buoyancy flux parameter is dependent on your gravitation, acceleration due to gravity, your velocity with which your plume or gas is releasing from your stack. Okay, this is V. Then ds is nothing but the diameter of the stack upon 2. Then Ts is the temperature of your gas that is emanating from the emanating from your stack. And then Ta means your temperature of your ambient air. Ts again the stack temperature. So if you have parameters of the stack, for example, if you have the stack temperature, if you have stack velocity, if you have stack diameter, then you can easily calculate this buoyancy flux parameter. So if you have buoyancy flux parameter, then obviously you can calculate this delta H, that is the plume rise. So first thing we have calculated, that is plume rise. Okay. Then second thing, we want to calculate the wind velocity. So how we can do this? Wind velocity at some height can be calculated if we have wind velocity at some height, at some reference height. For example, because you know anemometer or you have some instrument of which the height is 10 meter. Okay, so at 10 meter height by the instrument you have some value of the wind velocity. So that will be your U node. Okay, so you have the value of U node. You have the height that is 10 meter, that is Z node. Then if you want to calculate, let's say the wind velocity at 20 meter, then your Z will be 20. And we have a parameter that is P. We will also know this from where this comes. Then if we have such values, then we can calculate the wind velocity at that height, let's say to the 20 meter. Okay, but this P, what is this P? This P is nothing but this P is a factor that depends on your atmospheric stability. So we will see this. Okay, So if you have stability class A, means your atmosphere is very unstable. Then if it is a rough terrain, then the value of this P will be 0.15 for the urban area and 0.07 for the rural area. Okay. If you have the moderately unstable stability class, then your value will be 0.15 and 0.07 for urban and the rural respectively. If you have stability class C, that is slightly unstable, then your value will be from like 0.20 and 0.10 for urban and the rural respectively. So likewise, you have some value of the P. So if you know the stability class, you can easily find out what will be your value for this P. And these values are for the rough terrain. But if you have some smooth terrain, then you have to multiply this value with zero point 0.6. Then you will get the P value. Okay, so you have P value, you have initial wind speed, let's say, and the 10 meter, and you have the wind speed at the 10 meter. Then you can easily calculate the wind speed at the desirable height. Okay, so right now you calculated the plume rise, that is delta H. You have calculated the wind velocity at your height, at your desired height. Okay, then the third thing is you have to calculate the horizontal and vertical standard deviation. Okay, this can be calculated if you have the distance of the receptor from your stack. For example, you want to know the concentration at 1 kilometer from your plume or from your stack. So here your distance in x direction. So your distance in x direction is 1 kilometer. For that 1 kilometer, you can, from that graph, you can calculate the horizontal and vertical standard deviation. Okay, this is the exponentially graph. Okay, so you have calculated the plume rise, you have calculated the wind speed, you have calculated the horizontal and vertical standard deviation. Now we have the formula. So this is the Gaussian plume model equation by which you can calculate the concentration. So in the left hand side, you have concentration, and the position of that concentration will be x, y, z. So you want to see like where you want to estimate it, at what height you want to estimate this concentration, at what distance, and what's your horizontal deviation at which you want to see your concentration. So this concentration will be equal to, so here we have some parameters, that is q is the contaminant emission rate. If you have that rate, then you have wind speed, you have standard deviation in x and y direction, you have you have distance in x direction, if you have distance in y direction and z direction, then after applying this equation, you can calculate the concentration at the point you want to calculate. Okay, so this is how we can calculate this plume concentration with the model that is known as the Gaussian plume model. Okay, so this is the brief introduction about the Gaussian dispersion model. Okay, so based on that, this is just the starting. Based on that, we have the MCQs, and now we will try to give the answer of it. Okay, so the first question is, what is the standard unit of the standard deviation of the vertical distribution of plume concentration? So option I have is meter, meter per second, gram per second, microgram per meter cube. So what should be the answer? Can you please give me in the chat box fastly? I'm just saying. What do you think? What should be the standard unit of this standard deviation in the vertical distribution? Can anybody give me the answer of it? A, B, C, D? Jack Krishnan gave me answer A. Okay. Anyone else? Alka gave me answer A. Nishant also gave me answer A. Jyoti Verma gave me answer A. Okay, so if you four people have gave me the answer A, then yes, answer should be A. And the thing is, we already have discussed about this standard deviation in vertical profiling. Means this is nothing but how your plume is dispersing in the vertical direction. Okay, you have some center line. At some point, there is a maximum concentration, and if you will go away from that, either it in the upward direction or in the downward direction, your this concentration will be diluted. Okay, and because we are talking about this standard deviation, then this is related to the normal distribution. So let's talk about something like that. Like uh, at center you have mean. Okay, mean means you have maximum values lie within that area, and if you are going away from this, then what will be happen, your lesser the value will be here at the corner of it. Okay, so this is the graph of the normal distribution and the standard deviation. So in the plume, at the center line means at some height we have the maximum concentration, and whenever we will go upward or downward, then we will have the lower concentration. Okay, so this is the standard deviation, and we will measure it in the meter. So this is just for the sake of letting you understand. Then yeah, this is the if you can see sigma z. So sigma z is nothing but it is a from center line up to what height you have the concentration. Okay, this will be your this will be your standard deviation in the vertical direction. Okay, again, this is nothing. This is just to trying to help you understand. Okay, beside this, you must know some other SI unit or the unit for some other quantities. For example, for the concentration, our unit is meter, meter per meter cube, gram per meter cube, or we can also say microgram per meter cube. Then for the emission rate, the unit is gram per second. Wind speed, as you people already know, meter per second. Standard deviation, either in the horizontal or in the vertical direction, your unit will be meter. Because if we are talking about the height, either it is a stack height or the plume rise height or the effective stack height, the value will be only in the meter because it is the distance. Whenever you are calculating some concentration at some point in the x direction, then this distance will also be in meter. Your your dispersion in y direction, then this will also in meter, and the dispersion in vertically, then this will also be in the meter. So these are another units that you have to consider while calculating or solving some kind of numerical questions. Okay, so I have second question. Which of the following assumptions are associated with the Gaussian plume model? So I have four statements. The first is there is no diffusion in the x direction. Second is uniform continuous emission rate. The third is shape of the plume is conically. And fourth is the pollutant are non-reactive gas or aerosols. So select the correct answer. So what should be the correct answer? Nishant gave me answer D. Okay. So Nishant, according to Nishant, all the statements are correct. Alka gave me answer D. Okay. Jyoti also gave me answer D. You people are so expert. Like every time you people gave me right answer. Anyway, so the answer is D. All of these statements are correct. So, okay. So here, like we have three or four statements. First is there is a no diffusion in x direction. So what do you mean by x direction, and what do you mean by like diffusion? What's the definition of the diffusion? Secondly, if you have uniform continuous emission rate, what do you mean by the emission rate, and how it can be continuously? Then the shape of the plume is conical. This is very much clear. Then pollutant are non-reactive gases. This is also clear. So let's talk about more this Gaussian plume model and their assumptions. Okay, so the first assumption is plumes spread result primarily by the molecular diffusion. So what do you mean by this molecular diffusion? Molecular diffusion is nothing but, as here, yeah, this is the 7th 8th class content, where if you have the molecule of, let's say, water, and if you will add dye into it, then this dye will diffused evenly in this water molecules. So this is the diffusion. Okay, so so our first assumption was that our spread results primarily by the molecular diffusion, and this spread will be either in the horizontal, in the y direction, or in the x direction. Okay, but sorry, y direction and z direction. But if you people are talking about the x direction, then we are assuming that there is a no diffusion in x direction, but wind is moving, and this wind is pushing this plume to a smoke in the x direction. Okay, so there is molecular diffusion only in the y direction and the z direction, but not in the x direction. X direction is nothing but the direction in which the wind is flowing. Okay, so this was the first assumption. The second assumption is the time required for the pollutant to travel to the receptor is neglected. So here the concentration, change in the concentration per change in the time, we are assuming it zero. Means we are not considering time here to calculate to let this pollutant to travel to the receptor. So here we are assuming that there is a steady state. Okay, steady state means the change in the concentration upon change in time is equal to zero. The third thing is, we are assuming that we have the normal distribution of the horizontal and vertical pollutant concentration in the plume. Normal distribution means at some point at the center of it, we have the maximum pollutant, but as we will go from this center line, we will have the diluted concentration. Okay, in the horizontal as well as in the vertical direction. So we are assuming this. Then we are assuming that there is a no diffusion in x direction. We already have talked about this. Then the uniform continuous emission rate. We are assuming that our emission rate, the rate with which this plume is coming towards the receptor, it is constant. For example, it is 5 meter cube per second. Okay, so we are assuming, but this is these are only the assumptions, these are not the reality, and we are assuming such things to make our equation very simplified. Otherwise we need supercomputer, we need we can't calculate it manually. Okay, so that's why we have to do some kind of assumptions so that we can get some rough ideas about it. Okay, so and more assumptions we have is, okay, here we are assuming that our wind speed is constant up to the receptor. For example, in near to the chimney, your wind speed was 30 meter per second, and we are also assuming that at the receptor this wind speed is 30 meter per second only. Okay, so here we are assuming that wind speed is constant. We are also assuming that terrain is flat. If we are not assuming this, then there will be turbulent, and considering that turbulent in the equation will be trickier for us. Okay, that's why we are just assuming that our terrain is flat. Then we also assuming that pollutant dispersions follow normal statistically distribution, as we people already have talked about it. Then the shape of this plume is conically. We people know that we do have different type of plumes. It can be fanning, it can be coning, it can be like the fumigating plume. It can go up and down. It can have the snake shape, uh, then but right now we are just assuming that our shape of the plume is conically, so that there will be simplified equation. Then the pollutant are not a non-reactive gas or aerosol. Why we are assuming? If we will assume this this photochemical smoke formation secondary pollutant, then again this will be difficult for us to incorporate all these chemical reaction into our equations. Okay, so that's why we are just assuming that our pollutant are non-reactive gas or the aerosol. Then we are also assuming that plume is reflected at the surface with no deposition or reaction with the surface, just to simplify the equation. So we have these 10 assumptions on which we developed the equation. Okay, the third question I have, the expression for the determination of concentration C of a pollutant using the Gaussian dispersion model for a line source. Here we are talking about this line source, and here if you can see that sine theta. So in that above equation, this equation will be valid in what condition? So we have four: whether this this theta will equal to 0 degree, this theta will equal to 20 degree, or more than 20 degree, or the less than 20 degree. So what should be the answer? Nishant gave me answer C. Okay, Alka gave me answer C. I'm expecting more answers. Okay, Jyoti gave me answer C. Okay, if you people have already gave me answer C, then answer is obviously C. So because we talked about the line source, up to now we talked about the point source. Okay, so if we are talking about the line source and the associated model to it, so we have to understand what do you mean by this line source, what different assumptions we are assuming for this line source, how this formula derive, though we will not go up to that level. So, and why this is more than 20 degree. So, this is like, for example, there is a road, and in that road, vehicles are moving, and these vehicles, because this is forming a line. Okay, so for that we have to calculate how much concentration they are emitting at some point of at some point. Okay, so here we will consider that. For example, the car is moving in y direction, but we are assuming that wind is moving in the x direction, that is the perpendicular to the y direction. Okay, so these are the assumptions. The first thing is we are assuming that our car is moving, or our line source has a infinite length. Okay, the first assumption. The second is our wind direction is vertical to this direction of the moving of our line source. Okay, so this is what we are considering in the line source model. Then we have three assumptions. The first assumption is ground level surface. So we are not assuming that our line source is at some height. Okay, we are just assuming that our line source is at the surface only. Second thing, infinite length source of the ground level. So we are assuming that our the length of our line source is infinite. Then third is our wind is blowing perpendicular to the line. Okay, we have some example. For example, motor vehicle traveling along a straight section of the highway, or agriculture burning along the edge of a field, or the line of industrial sources on the bank of river, etc. So these are the examples. So basically you got to know what different assumptions we have, and what the direction of the wind speed with respect to the moving car. Okay, so we have this formula. Okay, and in this formula we can see we have the sine theta, and this theta is nothing but this is the angle of the wind. Okay, this wind angle can be 0, can be 90 degree. Okay, so if it is less than 0, okay, less than 0 means this will give you the uh, infinite value, because at the denominator you will have value that is near to 0, then this concentration will give you the finite value. Okay, and this is not the possible. So that's why based on some research, authors told that this theta value should be more than 20 to avoid this infinite concentration level. Okay, so that's why this is more than 20 degree. Okay, the fourth question I have: what is or are the disadvantages of using the Gaussian plume model for area source? And the options we have: require large amount of input information, consume large amount of computer time, and involves complexity. So what uh, select the correct answer? A, B, C, D. And we are talking about the disadvantages. Nishant gave me answer D. Jyoti gave me answer D. Alka also gave me answer D. Neha Sharma gave me answer D. Okay, so answer is obviously D. So because if we are talking about this area source, we need a lot of inputs. Okay, based on that only we can calculate this. So that's why we require large amount of input information, because each this area, if you will calculate it using the model, you will have the some spatial data. In that spatial data, this spatial data has been converted into the grids. At each grid you must have some value. You must have the value of the emission rate. Okay, you must have the value of the stack height. So a lot of information you need for this area source. So, and this will obviously, if you will have a large amount of input information, then you must have the supercomputers to calculate it, and this will also includes the complexity. So your answer was right. That is uh, a D, or it was, what was the answer? Answer was D, right? Okay, we already have talked about this, but because we have the question, so we have buoyancy flux parameter that is used to calculate the effective height of the stack, and the formula is given here. So the question wants to ask you the unit of F. Okay, Alka already gave me answer C before letting me finish. Nishant gave me answer C. Neha gave me answer C. Okay, so Jyoti also gave me answer C, and obviously answer is C. That is that is meter raised to power 4 upon second raised to power 3. So let's talk about more about this, because this formula is used to calculate the effective height of the stack, है ना? So effective stack height is nothing but this is the summation of the plume rise plus में stack height. Okay, and because if you want to calculate this plume rise is nothing but it is defined as the height above the stack orifice that the plume center line arises due to momentum and the buoyancy of the stack rise. Here you can see the delta H. Delta H is nothing but the plume rise, and if you want to calculate it, then you must have some value of some controlling factors, and these controlling factors are the factor related to the stack. For example, the shape, the size, the height of the stack, then the meteorological condition, what the ambient temperature, ambient air temperature you have, wind velocity, and the nature of the effluent itself. What's the temperature of that plume? So if you have that kind of values, then you can calculate your plume rise, and this plume rise can be calculated by various equation. For example, you have the Holland equation, in which you have velocity of this stack gas velocity, then diameter, then velocity, wind velocity, then the temperature. So you have lots of equation by which you can calculate this plume rise. You have Davidson and Bryant equation. Then you have the Stumke formula, by which you can calculate this plume rise, and you also have this formula. This is 150 F uh, upon mean wind velocity raised to power 3. Okay, and here F, as per the question, this F is the buoyancy flux parameter, and here the unit is meter raised to power 4 upon second raised to power 3. And how this can be? Here we can see that for the acceleration due to gravity, the unit is meter per second square, right? For the velocity, we have the meter per second. For the diameter of the plume, or diameter of the stack, that is meter. Okay, and because it is square, then we will square it. Then this temperature can either in Celsius or in Kelvin. So this is K upon K. So whenever you will cancel out some of the units, then you will get a meter raised to power 4 upon second raised to power 3. Okay. Okay, next question is, to calculate the maximum concentration using the Gaussian plume model, sigma z is given as a, so I have this square root h upon 2, h upon square root 2, h upon 2, h square root 2. Nishant gave me answer B. Okay. Neha gave me answer B. Jyoti and Jai Krishnan also gave me answer B. Okay, Alka gave me answer B. Answer is obviously B, and how it is, we already have cleared about this standard deviation in the vertical direction. Okay, then if we want to calculate the maximum concentration, so for that you have to consider that, because it is a normal distributed means at some mean point or at some center point you will have the maximum value. Okay, so it means if you will go in the horizontal direction, your concentration will be diluted. Okay, and your concentration will be lower. So here we are assuming that y is equal to 0, and the y standard deviation, standard deviation in y direction is also 0. Okay, but if we are talking about this z in the vertically, it may be possible that at some height you have the maximum concentration. Okay, but at what height? Okay, we have to calculate. And because if we are talking about that particular height, means we have to again estimate the standard deviation in that vertical direction. So what should be it? Then it should be h upon me root 2. So okay, here we can see that for a given x, the maximum concentration is at the plume center line. It can't be diverted. If it will be diverted somewhere else, our concentration will be decreased. Okay, and plume, so maximum concentration is at the plume center line, and it will decrease exponentially away from the center line at the rate dependent upon the sigma values, that is sigma y and sigma z. Okay, and because we already talked about it, that this concentration cannot be in the some y direction. Here we have to assume that y is equal to 0. Okay, because this concentration will decrease exponentially if it will go away from this center line. Then the distance to maximum concentration is at the distance where our standard deviation in vertical direction will be equal to height height, this is the effective stack height upon raised to power upon a square root of 2. Okay, then this equation is strictly correct if there is a ratio of the standard deviation in the vertical direction and the x direction, if this ratio is constant with the distance. Okay, and here if we can see that we are assuming that our x direction and in the z direction we have the value 0, then we will calculate this maximum ground level, and this will always occur in the center line. Okay, come to the next question. As a part of atmosphere that behaves in a coherent way concerning the dispersion of air pollutant is known as. So I have option. The first is pollution potential. Then second is atmospheric stability. The third is ventilation coefficient, and fourth is air shed. So what is the correct answer? A, B, C, D. Jay Krishnan gave me answer D. Alka gave me answer D. Neha D. You people already know about this answer. You people, either you people are learning very quickly, or you are taking class very seriously. Anyway, but this is good for you that you people know the answer. So answer should be exactly D. Okay, so let's know something about this air shed. Okay, so what do you mean by this air shed? Just like the watershed, uh, this air shed is also consist of some geographical area, and that geographical area has some common characteristics of the air pollution emission. For example, at one point, our the concentration of air pollutant will be equal to the concentration at let's say the B point. Okay, so at every point the concentration will be uniformly distributed. So if this is the condition, then we will call that particular area an air shed. So according to the definition, it consists of a geographical unit that have the common characteristics of the air pollution emission source and wind flow pattern. For example, if at that particular location wind is for example, there is a particular wind direction. Okay, so it will give you the pollutant uniformly in that direction. But for example, in some another location, the wind direction is opposite, so the characteristics of the air pollutant will be different at that location. So that's why here we have the common characteristics of this wind flow pattern, and it may be due to topography or it may be due to meteorological constraint, and even because of the topography and the meteorological constraints. Okay, so here we can define this air shed as a part of the atmosphere which behave in the coherent way as per your MCQ with regard to dispersion of pollutant. Okay, and this can be range from small area with fewer polluting sources to large metropolitan agglomeration with the complex air quality problem. So your size of that air shed can vary. It can be very like small area, and it can also be the very large area. Then how we will define the boundary of our air shed? Okay, so based on our problem, we can define air shed differently. Okay, so for example, air shed can be defined as per the geographical region. Okay, limited geographical region. For example, you have a small valley. Okay, if you will go outside of that valley, you will have different air pollution emission sources, and the air pollution characteristics will be different out of that valley. So this air shed has been limited by some geographical reason, so by which we can decide the boundary of our air shed. First is by the geographical region. Okay, so here the air shed can be a limited geographic region such as small valley community in which dispersion of air pollutant is limited by the topographic constraints such as surrounding hills and the water bodies. The and here because whenever you are burning the chulas or something, so this pollutant will not disperse out of your valley, but these will be only confined within that valley. So this will give you some common characteristics of that area. So this is the one way by which we can decide the boundary of the airshed. Then airshed can also be large geographic area covering hundreds of square kilometers because of similar type of pollutant emission, topography and meteorology. As a result, it experiences similar air quality issue. For example, in some area, let's say Solan in Himachal Pradesh, where there is a lot of factory related to the pharmaceutical. There are thousands of factories that are manufacturing the medicines. So that area will have a that area may also act like the line area source. Okay, and that area source, we will have a very similar type of the pollutant emission, and that's why that area we can also define as a airshed. Then the boundary of airshed can also be based on the administrative consideration. For example, as a Delhi is an administrative boundary, and we can also consider this Delhi and the administrative boundary of Delhi as a airshed boundary, or the we can also delineate the our airshed, right? Uh, then we have three steps by which we can decide our boundary of that airshed. Okay, so how we can calculate this? So the first step is quantification of emissions to prepare a multi-pollutant emission inventory. So what we will do, at some distances, we will prepare our emission inventory. For example, in Delhi, we went to Chandni Chowk. Then in Chandni Chowk, we calculated the emission. What is the concentration of the CO2 that is producing from the, let's say, Chandni Chowk. Then we went to the Jama Masjid area. Then we also calculated how much concentration it is emitting. Then we will have the emission inventory at various locations. Okay, then we will also collect the meteorological condition. We will see whether in Chandni Chowk and in the Jama Masjid area, either there is the direction of the wind is same or not. Whether and we will also see whether the emission source is giving the same concentration in the Chandni Chowk as well as in the Jama Masjid. If this is the condition, if we have the similar meteorological condition, if we have similar emission sources, then we will call it as the airshed, because it has a common characteristics even in the Chandni Chowk and in the Jama Masjid area. So the first thing is we will prepare this emission inventory. Then we will collect the meteorological data, and then we will prepare the air quality level using air quality modeling tools, and then we will see the dispersion and the dispersion to the reactor. And if we have the common characteristics of the air pollutant in that area, and we have the common characteristics of the meteorology, then we can define that area as a airshed. Okay, so this is the method by which we can delineate an airshed. Okay, the next question I have, the available assimilation capacity is given by. So the first is, uh, okay, Alka gave me answer A, Nishan gave
Difference between permissible standard and ambient pollutant concentration. A.
yeah, yes, Finak, exactly. You are giving me right answer. So here the question is, what do you mean by this permissible standard? And second is, what do you mean by this ambient pollutant concentration? After only we will get what do you mean by this available assimilation capacity. So, and what do you mean by NAAQS? So can anybody tell me what's the full form of this NAAQS?
National air quality of I mean National Ambient Air Quality Standards.
Yes, so this is nothing but the National Ambient Air Quality Standard. Okay, so these are the standards. We have given some value of some pollutant. If we will cross it, then this will be the violation of the standard. Okay, for example, if this is sulfur dioxide, then in the residential area, this should not go more than 50 microgram per meter cube. And if it is going up to that, it means it will give you some adverse effect. Means, for example, your permissible standard is giving the sulfur value is 50. Okay, but right now your ambient pollutant concentration for sulfur dioxide is 60. It means the capacity of the assimilation, or you are crossing your permissible standard, means it will give you the adverse effect. Whatever was the capacity of your atmosphere to have that sulfur dioxide in your atmosphere, that will not give you the adverse effect. You are just crossing that. So this is the by which, if you will subtract this ambient pollutant concentration to the permissible standard, then this will give you the assimilation capacity. So here we will see some of our pollutant that have the that have some standard. Then we will also see what do you mean by this assimilation capacity, again with some definition. So yes, the answer is A. Okay, so we have how many criteria gas or the pollutant we have, of which we have given this NAQS. Can you people tell me how much criteria pollutant we have? Yes, Alka. We have 14, sorry, we have 12 pollutant, of which we have given the values. Okay, if we are crossing that value, means we are violating it. Okay, so what are these pollutants? These are sulfur dioxide, nitrogen dioxide, then particulate matter 10, particulate matter 2.5, then ozone, lead, carbon monoxide, ammonia, benzene, benzopyrin, arsenic, and the nickel. For that, we have different values for the industrial, residential, rural, and other area, and different value for the ecological sensitive area. And this, because if it is a ecological sensitive area, then your standard value should be lesser. Okay, because within even a small concentration can give you the impact on the biodiversity and some other means. Okay, so here we have some value. For example, for sulfur dioxide, it is 50 and 80. 50 for the annual, 80 for the 24 hours monitoring. Okay, and likewise you have some values from sulfur dioxide to the nickel, for industrial as well as for the ecological sensitive area. So these are our standard values that are given by this NAAQS. And who prepared this NAAQS? Can you tell me the name of the agency? Who prepared?
From CPCB,
Yes. And full form of CPCB is?
Central Pollution Control Board.
Exactly. So Central Pollution Control Board, based on a very rigorous research, gave you some standard. If you are crossing in any city, then this city will be known as non-attainment city, and some fine can also be implied on that city. Okay, so this is nothing but the this is the permissible standard given through this NAQS. And ambient pollutant concentration you will calculate every day, and if you are subtracting it, then this will give you the assimilation capacity, right? uh, okay, so I have the definition of the assimilative capacity. So this is nothing but this is the maximum amount of pollution load that can be discharged into it without violating the best designated use of the air resources in the planning region. So this is how much amount of the pollutant you can release into the atmosphere. So this is the assimilative capacity. And uh, if you are allowing some companies, or let's say some industries, to release that pollutant in the atmosphere, it means atmosphere already have some cleaning mechanism, okay, to clean that pollutant from this environment. And the mechanism may be dilution, that may be dispersion, and the deposition. So dilution is as your air will go away from some center point, then obviously this will be diluted. Then dispersion, as we talked about it, because of diffusion and all. Then the deposition may be due to the dry deposition or the wet deposition. For example, if you have rainfall, then this rainfall will bring the particulate matter down to the ground, okay. So we have different mechanism by which our atmosphere itself can clean itself, okay. And that's why we have some uh, potential in the atmosphere itself, that we can add some pollutant into it, okay. But we can't add much, because it has a limited assimilative capacity, and if you will violate it, then obviously you will have some adverse impact on your health, on human health, on animal health, and even on your building, and or even on the plants, okay. So this is the assimilative capacity. Then how we can use this, how we can take the use of the assimilative capacity. So this can be important tool for suggesting the safe limit of disposal of pollutant for industrial operation, as well as for area based management of air pollution, and to mitigate the pollution level. So for example, if you want to install a industry at some area, so you have to consider into the assimilative capacity of that particular area, of particular airshed. Maybe if it is a valley, for example, if it is a valley, then it may be the assimilative capacity of that valley is lower than, let's say, to the plain area. Why? Because the wind will be stagnant at that valley area, and it will be not very easy to disperse your pollutant in the valley area, okay. So you first have to consider what's the assimilative capacity you have before installing the industry at that area. Based on that, you can mitigate the pollution level, okay. And then you may also know how much amount you can release, how much amount of the pollutant you can release into the atmosphere. Then it is an indicator of the potential for future growth, keeping in mind the resource such as air, water, land, etc. So if you know the assimilative capacity, for example, you have constructed the hospital, you have constructed the a school at one position, and right now you can also build something, because you have the remaining assimilative, you have the available assimilative capacity at that area as well. Then you can also construct some more infrastructure there, because you have some available assimilative capacity, okay. So the more you have the assimilative capacity in that area, then this is the indicator that you can construct more infrastructure there, okay. Because you haven't crossed your national standard of that particular pollutant or pollution, okay. So this is the use, okay. So but how will you calculate this assimilative capacity? You have calculated the available assimilative capacity as you subtract your ambient air pollutant to the standard, okay. That was the available assimilative capacity. But if we are talking about the assimilative, then how we will calculate this? So we have two approaches by we can calculate. The first is ventilation coefficient, and the second is pollutant potential or the dispersion potential. So what do you mean by this ventilation coefficient? And this ventilation coefficient is directly proportional to the assimilative capacity of the atmosphere. And we will see the formula of this ventilation coefficient. Then if we are talking about the pollution potential and the dispersion, so pollution potential is inversely proportional, and dispersion potential is directly proportional to the assimilative capacity. And the second approach can be estimated through some dispersion model. Okay, and the first by using the meteorological parameter, that is the ventilation coefficient. Okay, so what do you mean by ventilation coefficient? So this is nothing but this is the product of mixing height. Mixing height is Z multiplied by the average transport wind speed within the mixing layer. So again, the question is, what do you mean by the mixing height? So can anybody tell me what do you mean by mixing height?
Concentration of pollutant vertically in our atmosphere.
No, this is some kind of height.
Yeah.
So what height it is? You can guess. So this is the height up to which our plume, or let's say smoke, can disperse. Okay, so this is that height. This is like this is the height upon where our pollutant or the plume can mix. Okay, so like this is the unstable. If you have read about the atmospheric stability, then this is the layer where we have the layer is not stable, means your plume can rise vertically. So mixing height is nothing but up to the height up to which our plume can rise vertically. When our plume will not rise vertically, it will start either moving horizontally, or it will stop moving
You
vertically.
mean to say lofting plume?
These are like lofting plume is a different plume, but I'm talking about just the height. Okay,
Okay.
so
The
so
height.
so for example, up to 2 kilometer, your plume can rise vertically, and after that, air will be that much cold that your plume can't rise vertically. Okay, so mixing height is that height up to which your plume can rise vertically. So if you have that height, and how we can calculate that height? If you have ambient lapse rate, and if you have the dry adiabatic lapse rate, we will plot it where these two plot or these two graph will intersect to each other. That will give you the mixing height. Okay, so if you have mixing height, if you have average wind speed, if you will multiply it, then you will get the ventilation coefficient. And higher the ventilation coefficient means more dispersion is possible. If you have lower ventilation coefficient, means your air will be stagnant, pollutant will accumulate at that area, and this will give you the pollution in that area. So and your assimilation capacity will be reduced. So this is the ventilation coefficient. So this is the product of mixing height and the wind speed. And this is act like only the indicator of the air pollution dispersion. So whether your air pollution will disperse or not, it will depend on your ventilation coefficient value. But this is just the indication. It will not tell more about the air said assimilative capacity. But this uh, the different things that we had, for example, this pollution potential and the dispersion potential that we can estimate from the model, this will give you a very true idea about the assimilative capacity. But ventilation coefficient is just the indicator of it, not giving you the true values. Okay, the ninth question we have, the basic equation for emission estimation is, so emission will be equal to what? So there is a relation between emission factor and the activity data. So Alka gave me answer C.
Yes, ma'am. Multiplication of emission factor and activity data.
Yes, answer should be C. That is emission factor multiplied by the activity data. So what do you mean by emission? What do you mean by emission factor? And what do you mean by activity data? So we will know about it, right? Answer is C. Okay, emission is how much emission you are getting from the source. Emission factor is, it is the average rate of the emission of the pollutant per unit of activity area. Okay, for example, you are for example, if a car is moving, Okay, and you are calculating in 1 hour, or let's say at 1 meter, at 1 meter length, how much emission it will give to you. So this is the scale. After that, you can multiply. For example, if you have thousands of car, then you will multiply with that scale factor. So this is the emission factor. Okay, so emission factor is nothing but this is the average rate of the emission of a pollutant per unit of activity data. For example, for one car, how much pollutant we are emitting, okay, from the source. And if we have thousands of such car, then we will multiply it. Well, okay, so this is the emission factor. Then the activity data, this gives us a measure of the scale of activity causing the emission. So we will know, like, by vehicle you can have the pollution, for while from that chimney you may have the pollution. So you will see what activity data you have. For example, from the agriculture you may have some kind of pollutant that will emit into the atmosphere. So we will list out the activities, then each activity at that particular area, what the average rate of emission, and then we will multiply our whole activity data, then this will give you the emission. uh, Laboratory way. Okay, so emission factor, this is the average representative value that attempts to relate the quantity of air pollutant released to atmosphere due to a particular activity associated. And this may be expressed as mass of pollutant divided by a volume or the weight of the raw material. So this is your emission factor. Then activity data, this is defined as the quantitative measure of the activity that associate with the emission of air pollutant. Okay, so here we may have the activity data. For example, from transport, what different vehicle category we have. Either it is a three-wheeler or four-wheeler or two-wheeler. Either it is based on like what type of fuel we are using. Either we are using diesel, petrol, CNG. So we will categorize this under this transport. So this will be the activity data. Then, for example, for the waste burning, how much quantity we are burning per capita. For example, the diesel generator, the fuel used for the number of hours. So these are the example of your activity data for different sources. Okay, so the next question is related to emission again. So this is the definition of something. So the definition is the comprehensive stock of all the pollution emitting sources and the emission in a given region with a specific time period is called. So you have
Emission
to,
inventory.
okay, emission inventory. Alka gave me also answer A. I'm expecting more answer. No one is giving me a wrong answer. I don't know why.
Ma'am, because these are already done in assignments.
Okay, are you people attending like different? Like two people are also solving that assignment, right?
Yes, ma'am.
Yes, ma'am. Same questions.
Yes, because these are the questions that like these are the previous year assignment question, and we all are accessed by these questions, so we are taking this question. But yeah, I will try next time to give you new questions. So I don't think that this is that much benefited to repeat all these previous year's assignment question. Anyway, next time I will try. Okay, so you people gave me answer A. So exactly answer should be emission inventory. So what's the definition of it? So this is nothing. This is invention. Inventory is estimated or calculated for a given region. Means you must have some specific reason for a specific time period. For example, for 1 year you are calculating, and this is comprehensive stock of all the pollution emitting sources. For example, vehicles. For example, industries, power plants, road dust, construction dust, and a lots of things we have for that region. For that particular period, we will calculate for some particular pollutant. For example, for carbon dioxide, for example, for the Delhi, for let's say 1 year, we are calculating how much carbon dioxide was released from Delhi in 1 year. So this will be nothing but the emission inventory of the carbon dioxide. And carbon dioxide is just one pollutant. We can also classify different type of gas or pollutants, and we can give the emission inventory of it. And the like emission inventory can be in a different way. For example, we can give the value uh, pollutant wise. We can also give the value like activity wise. For example, from transportation, how much emission we are getting, or we can give the area wise, like for example from Delhi, how much pollutant emission we are having. So like different like we can use this emission inventory according to our problems, right? Okay, so this is the one example of emission inventory. So in the left hand side we have pollutant list, for example benzene, methane, carbon monoxide, carbon dioxide, and then we are calculating how much ton of this pollutant uh, is releasing per year. And this is I think for the California. So and this is based on your vehicle. So either if either you're working is car or bus, so how much car is giving you the pollutant, how much bus is giving you the pollutant. So this is like that. Okay, so based on that, so this is the emission from the vehicle types. You have different activity data. For that different activity data you can create your emission inventory accordingly, and this is important. For example, if you people know that your car is releasing more carbon dioxide as comparison to bus, then in the future what you can do, you can uh, uh, because introducing some inventives or the innovative techniques or the innovative things or the engine in the car in such a way that you can reduce your emission from the car. So so preparing such type of emission inventory is very important for us. Then this is different. For example, it is giving you how much emission is from residential area, from agricultural area, from electricity, and this is also from the data is also from the California only. So this is giving me the carbon dioxide equivalent. So how much million ton megaton it is giving me activity wise. So this is also the emission inventory. So this is a different way. And because we can take the use of different type of inventory in a different purpose, so that's why we have a variety of emission inventory. Then this is the use. Here we can see this is again for the California. So the transportation emission is reducing. Let's say for the electric power, with the time, with the period, the emission is reducing. So and in somewhere it is increasing. So we can get an idea like how we can make the use of this emission inventory in the future. So we must have continuously data for each year or for each season, so that we can have and we can act to mitigate the pollution. Okay, then I will not go into it. Like these are the different advantages of preparing that emission inventory. So this is like, oh, what's the use of this emission inventory we may have. Okay, so utilization of the emission inventory. So the first thing is quantitative understanding of the actual emission. So you must have the data of the actual emission in a very quantitative way, so that you can help in the policy making. Then the modeling activity. For example, you want to uh, with the help of the air modeling, you want to know the air pollution at some level. Okay, so how will you know? You must know at what source, what type of pollutant you are getting and in what amount. Only then, based on some meteorological condition, based on some underlying equation, you can calculate the pollutant at some receptor level. Okay, so for any type of air modeling activity, you must have the emission for that grid. Okay, so this is very important to have the emission inventory for the air modeling part. Then the future projection and the setting of the target. If you have emission inventory, let's say for the 20 years, and you know that this is your carbon dioxide because of the transportation is increasing, then you may have some future projection with the help of the air modeling, and you can also set some target. If it is increasing and your carbon dioxide will increase, then you must have the target to reduce it. So how you will reduce it? So you must have some kind of mitigative options for that. So you can set some target if you have the value of the emission. Okay, so that's why also you must have the emission inventory. Then the consideration of possible reduction measure, as in every point. After all, we want to reduce this pollutant from our atmosphere. Then yes, we will the possible reduction measure will be taken up only whenever we have the emission inventory. Then the planning of policy and measures and their follow-up. So this is just same like the fourth point. So this is the utilization of an emission inventory. And like different type of pollutant we can consider while we are preparing the emission inventory. It can be the toxic pollutant, for example particulate matter 2.5, particulate matter 10, carbon monoxide. It may be persistent organics, for example pH. What's the full form of pH? Can anybody tell me pH?
Logarithmic reciprocal of hydrogen concentration.
No, PAH. This is the persistent organic. P means polycyclic aromatic hydrocarbon. So under this persistent organics, we have PH, we have PCDD, PCB, pesticide. You will know about this, I think, in next assignment. Anyway, then greenhouse gases. We have carbon dioxide, methane, nitrous oxide, then fluoride compounds, then sulfur compounds. So these are the greenhouse gases. Then heavy metals. So the thing is that in the emission inventory, you may have a list of the pollutant, and based on your work, based on your problem, you can prepare the inventory of that particular pollutant. Okay. Then we have different approaches by which we can prepare this emission inventory. The first thing is bottom-up approach. Bottom-up approach means you will go to that particular, let's say the 10 sites. Okay, you will go to 10 sites, then you will collect how much pollution we are getting from that 10 site. Then we will collect the meteorological data. We will fix it each grades. Okay, so this is the bottom up approach. The second approach is top down approach. Top down approach is nothing but the reverse modeling. Means you have already you have pollutant in your atmosphere. Based on satellite, you will get the data, and then with the inverse modeling, you can estimate that pollution or that pollutant may come from that source. Okay, so this is the top down approach. Bottom approach is very good, but it is like very intensive in manpower. Like for that we must have trained people. We like there is a lot of input information we need to prepare this bottom up approach, but this will be very accurate. But if we are talking about this top down approach or the reverse modeling, then obviously this will be like it will be very quicker to estimate this emission inventory, but there will be higher uncertainty and there will be the loss of the accuracy. So these are the two approaches by which we can calculate this emission inventory. Maheshwari raised the hand. Do you want to ask some question, Maheshwari?
Yes, ma'am.
Yeah, yes, Maheshwari.
Tomorrow is my exam is going to be conducted.
What?
Tomorrow I have one exam, ma'am.
Okay, so you may leave, I think, because if you
Ma'am,
want to share, yes.
please give me your phone number, ma'am.
See, this is
Yes,
like
ma'am. Please give me phone number so we can contact you if there is any doubt or regarding something.
I can share you my email ID so that you can meet me. Can I share, Maheshwari?
Yes, ma'am.
Okay, so this is Jyoti, JYOTI 2121 @ICERB, that is IISERB, ICER Bhopal, uh, .ac.in.
Ma'am,
Ma'am,
your
write
phone
it
number,
in the
ma'am.
chat. Please.
I'm writing in the chat box.
Ah,
Okay, so I shared my email ID on chat box. You can check. Did you get Maheshwari?
another one time chat box open, ma'am.
What?
Another one time, ma'am. That is going out. Another one time.
I'm not understanding.
I am
Maheshwari.
I am having a பாதி தான் இருக்கு மேம் இன்னும் கொஞ்சம் வேணும் மேம் மேம் full email ID send ma'am.
This is full email ID, yeah?
This is the email ID is removed ma'am.
Oh, this is Jyoti21 @icerb.ac.in.
It's there, ma'am, in chat box.
Yes, it is there in chat box. You can have it, Maheshwari. Okay, so I think we should move. Okay, so I have one equation. That one equation is related to the estimation of the wind speed, and we have the formula. Here we have the P. So P is the factor that depends on. So we have four options: effective stack height, vertical standard deviation, horizontal standard deviation, and the atmospheric stability. So what should be the right answer? I think this is not from that previous year's assignment, so you can have some you have to think about it. What should be the answer?
Ma'am, I think effective stack height is there because x-axis and y-axis are representing horizontal and vertical. So I'm guessing that A will be the answer.
No, right now, because this is not among the assignment questions, so you people are giving the wrong answer. I'm happy that you are giving the wrong answer. So anyway, I give you one example. This is not just about the chimneys or plume. This is just like that. For example, at zero height, you have some wind velocity, but at, let's say, 1 kilometer, what will be the wind velocity at 1 kilometer height? So if you people know that your wind speed exponentially increases with the height. Okay, and this is not about the chimneys. This is just about your vertical profiling. Okay, so whenever there is an increment in height, the wind velocity will also increase. So here the p value will depend on upon what? Now you can estimate. Answer should be
Horizontal.
no. I told you, like, this is not related to the plume. So if it is not related to the plume, then effective stack height is not among the right answer, and the standard deviation will also not among the right answer. Why? Because we are just talking about generally how our wind speed will increase with the height. So answer should be D. That is the atmospheric stability. So for example, if you have the inversion condition, inversion means the temperature is increasing with the height. Okay, and if you people know that in inversion condition, like it is very difficult to move anything. Okay, so everything will be stagnant at that place. Okay, so and you have different type of stability, that is instability, you have highly absolute stability. So based on how your temperature is increasing or decreasing with the height, on which your wind speed will also dependent on. Okay, so answer should be D, that is the atmospheric stability. So here we have, like, the value are defined for different stability class. If we have a stability class, means if our atmosphere is very unstable, for the rough terrain or for the urban area, this value for P will be 0.15. For the rural area, this value will be 0.07. And likewise, if your stability class is B, then it will be the moderately unstable, and the value will be 0.15, and for rural area this will be 0.07. So P value is dependent on your atmospheric stability, and if we are talking about the smooth terrain, then this P value for this rough terrain, it will be multiplied by 0.6, and you will get the value of this P. So if you people know about the atmospheric stability, then you will also know the value of P. And after that, and if you know the value of this, U node is nothing but wind speed at some initial height. Okay, and Z node is the height of that from where you measured that initial wind speed. Okay, so these are the reference wind speed and the reference height, and based on that we can calculate the wind speed at some height Z. Okay, so this is dependent on the P value as well, and P value is dependent on the atmospheric stability. Okay, the next question. What is or are true about wind and its direction? So the first is, total concentration of the air pollutant is inversely proportional to the increase of wind angle direction with respect to receptor. Wind speeds generally increase with the height. Stronger the wind, the lower the plume rise. Wind speed affect the travel time. So what do you think? What should be the answer? A, B, C, D. And this question is not among your assignment. That's why you are taking time. But I'm happy that you are taking time. What should be the answer? Pinak, can you guess?
Ma'am, I'm like understanding one by one concepts that wind speed generally increases with the height, as you said. And third, the statement is the stronger the wind, the lower the plume rise. I think it is right. So I think D will be the answer, I guess.
Yes, D will be the answer. And Alka also gave me answer D, I think. Yes, Alka gave me answer D.
And for fourth, the wind speed affects the travel time. Yeah, it opposes in the opposite direction. If we move
Yes,
like that.
yes. This is just
I
like
think
that.
D is
If your wind speed will be higher, then it will take very less time to reach to the receptor. So third is also fourth is also correct. And if you are talking about the first, total concentration of air pollutant is inversely proportional to the increase of wind angle direction with respect to receptor. So this is also true. Because why? As your wind speed will be higher, this will disperse the pollutant, and that's why up to that receptor you will have a very low concentration of that air pollutant. So the first is also right, because if it
Please
will
repeat
be
first statement.
what?
I'm not able to understand the first one.
First one is, uh, uh, if your wind direction is uh, like based on your wind direction and based on your wind speed, your pollutant will be dispersed. Okay, so if you have high concentration at what point, but if there is a wind that is coming from backside of it, then what this wind will do, this wind will push this pollutant and will disperse. So this
Okay.
this is just like that. Because of wind, because of the wind angle, because of wind velocity, your pollutant will disperse, and that's why there is a inversely proportional relationship between that. The second is again because by that equation, we know that our wind speed will increase with the height. Then okay, then stronger the wind, the lower the plume rise. Why? Because uh, because this will inhibit our vertical rising, because always we consider wind in the horizontal direction. So if it there will be stronger wind, then it will resist the vertical rising of the plume, and this will lower our plume rise. Then the fourth is wind speed affect the travel time. As we all know, if it is in our direction, then this travel time will be lower, and if it is opposite in direction, then travel time will be more. So the answer should be D. Okay, what are the assumption for the line source plume modeling? So ground level surface, infinite length source of ground level, wind blowing perpendicular to the line, and Nishant gave me answer D. Alka, what should be the answer?
I will take a time.
Okay, okay, take it. Pinak, what do you think? What should be the answer?
Yes, ma'am. I will take a time too. But as per my understanding, I think D will be the answer because ground level surface is related to line source, and second, in line source there is an infinite length. I think, as I have seen in the videos, and there is a wind blowing perpendicular. So I think D will be the answer. Yes, ma'am. I will go
Yes,
for D.
yes, everyone gave me answer D. Nishant, Jyoti, Alka, and even you. And yes, the D answers. Monisha, you want to say something?
D.
Yes, answer is D. So we already talked about that. No? In my previous slide, we talked about this. For example, Monish, can you mute yourself? Okay. So in our previous slide, we talked about it that if it is a line source, then we have some kind of assumption to just simplify the equation. And our assumption is that if it is a line source, then we will assume that our line source will be only at the ground level, will not take any kind of height. The second thing is the length of that line source, we will consider it is a infinite. Monish, can you mute yourself? Yes. Okay. And then third is we are assuming that if car is moving in the x direction, then our wind will be blowing in the y direction. Means that is the perpendicular to it. And these are nothing but these are just to simplify the equation. So that's why D will be the right answer. That A, first, second, and third statement are the right. Okay, the next question. Initial spread, which while calculating area source plume concentration can be given as. Monisha, what's your question? Monisha raised here. Okay, Nishant gave me answer C. Okay, Alka, Jyoti. This is related to the area source plume and area source modeling. We will discuss it also at length. Answer should be C. Nishant gave me right answer. Okay, so we will see what do you mean by this. So here we have standard deviation in the y direction, and this is, we talked about it, initial, means we have some initial standard deviation and we have also the final standard deviation. So we will talk about it. Then we have the S. What do you mean by this S? Then we also talked about it, and the answer should be C. Here S upon 4 by 2, and we will talk about this Y. Okay, so first there is a area source. Okay, and if we want to model it, if we want to calculate from that area source how much concentration we are getting to a particular receptor, so again we have some kind of assumptions. So here the assumption is, we are just assuming that uh, pollutant is coming from only a single point. Okay, and this single point is a virtual single point that doesn't exist, but we have calculated that we have to calculate that virtual point source. That particular point source will give you the area source, and this area source will give you some kind of pollutant to the receptor. Okay, so here area source can be, for example, autos, homes, or the small businesses, or for example, I gave you the example of Solon. In that area we have hundreds of industries of pharmaceuticals, so that will act as a area source. So here I have figure. Okay, if you are seeing that rectangular area, this rectangular area is the area source from where we are getting the pollutant, and R is our receptor. So we want to calculate the concentration we are getting from the area. That area is in the rectangular form, and okay, so how we can calculate this? So we have to first identify a virtual point source. So here we have the virtual point source in the left side. Okay, so you have virtual point source, you have area source that is in the rectangular form, and you have R, that is the receptor where you want to calculate the concentration of the pollutant. Okay, so for that, and the length of this square is S. Okay, so this S is nothing but this is the side of the your square. Okay, then how we can calculate this concentration? So we have 3 or 4 steps. The first step is, first thing will be, you will calculate the distance of your where there is y and x is intersecting to the virtual point source. So how much distance we have from that virtual point source to your area source. So how will you calculate that distance? So this distance can be calculated by your standard deviation in the y direction. Okay, so, and how we can calculate this? This can be calculated by this one, S by 4 by 2. So if you have the side of the square, then you will divide it by the 4.2, then you will get the standard deviation in the horizontal direction. Okay, Alka ne tukka maar diya tha. Anyway, so after that you will so you will get the standard deviation. So this will be the initial spread. Okay, based on that initial spread, you will calculate the distance of virtual point source to the area source. And how you can calculate this? This can be calculated by some graph. Okay, in that graph, if you saw that in x-axis we have the distance, and in y-axis we have the standard deviation. So from that graph, you will get the distance between virtual point source and the area source. Okay, so you have x node, means this is your initial distance. So if you have x node, if you have xr, that is the distance from the area source to the receptor, then you will sum it, then you will get the total distance. Okay, then if you have the total distance, again you will calculate the standard deviation in y direction and the x direction based on the graph. And then if you have that value, then in that point source model equation, you will put that value and you will get the air source concentration for that particular receptor. So we will see here. Okay, here are some notations. X node, XR, and emission rate, side, and initial spread. So we have the unit of that. Then these are the steps. So first you will calculate the initial spread. Initial spread can be calculated by dividing this side of the square by 4.2. Then you will calculate the virtual distance. How you can calculate this virtual distance? If you have standard deviation, or if you have the initial spread based on the graph, you can calculate the virtual distance, that is x node. Okay, if you have x node, if you have xr, then you will locate your source. Then you will get the x value, means distance from that virtual point source to the receptor. And again, if you have this distance value, then you will again calculate the spread, and this again will calculate it using the graph. Okay, and then you will predict the concentration. So these are 4 steps by which you can calculate. And this is the graph. Here we can see in the x direction we have the distance downwind, that means in the x direction, and in the y axis we have the standard deviation in the horizontal direction. So by which, and based on the stability class, based on the numerical that has been given, and in which numerical, if you have given that particular stability class, so stability class can be either A, B, C, D, or F. So based on your stability class, based on the distance, how much distance you want to calculate to up to that receptor, and then the concentration, then you will get the value of the standard deviation in that horizontal as well as in the vertical direction. So you will get that equation from this curve. Okay, this was all. Next time I will try to give you some new questions, because yeah, I know that the last that live session already have such type of questions, and you people quickly give me the right answer.
What is the curriculum of this live sessions? Like sometimes is taken by you and other ma'am.
No. Every like we are 3 people, and we do have a particular time of taking that live session. So my timing is every time on Monday from 6 to 8, and another may have, I think one have on Saturday, and one have, I don't know about that, but yes, we 3 have different a particular time for this live session, and mine will always on Monday from 6 to 8.
Okay. That's
Yes.
because your like session is amazing. You are little bit responsive, and so we love to attend your ones.
Thank you so much. But yes, I will try to give you next time new MCQs, and yeah, I always try to like explain why the answer is correct. So based on that, I made some new slide to let you people understand. But yeah, thank you, Pinap, for that. If anyone have any query, you can ask me. Otherwise, we can leave.
Ma'am, the NPTEL video lectures are somewhat hard because the professor in that is like paraphrasing only, not able to explain it clearly, ma'am. I just say one.
Yes, this is true. Like sometime you may get the professor that are very they love to teach, and they try to let you understand in a very efficient way. But yeah, we can accept that